Assalamualaikum warahmatullahi ta'ala wabarakatuh and good morning. I'm Dr. Sabah Bau from the Physics section, Pusat Pengajian Pendidikan Jarak Jauh, University Science Malaysia. This is course JIF 318, Quantum Mechanics. We are in chapter 3, the Schrödinger equation. Unit 3.1 is on the introduction to the Schrödinger equation. The objective of this lesson is that you should be able to explain some fundamental aspects of Schrödinger equation. As introduction, Schrödinger equation was developed by Erwin Schrödinger and published in 1926. He was an Austrian, was born in 1887, died in 1961. He won the Nobel Prize in Physics for the work on Schrödinger equation in 1933. The equation forms the basis of modern quantum mechanics. Remember that previously we had discussed on the old quantum mechanics or quantum physics, old quantum physics. For example, when Niels Bohr put forth his postulates of orbital electrons, he used quantum physics basically for the discrete energy levels and also for the determination that no radiation is emitted by orbital electrons even though they are in constant acceleration. However, by putting the orbital electron at specific energy levels, then this contradicts the Heisenberg uncertainty principle. That's why we call those quantum physics as old quantum physics, while the modern quantum mechanics is based on Schrödinger equation. And it is one of the most important equation in all of physics. Basically, the equation looks simple enough, but actually the interpretation of the equation sometimes is against our perception. The way it describes the behavior of particles is fundamentally different from the corresponding description in classical mechanics. So basically the Schrödinger equation is completely a different field or different form of physics at all, especially in describing particles in microscopic physics. The difference between these two, in classical mechanics, a particle has a fixed position in 3D space given by the vector r. Okay, so for example, the wave functions psi here in terms of r, vector r, and t. So a particle in 3D space is fixed at a distance r from the origin. But in quantum mechanics, a particle no longer has a definite trajectory as the above. So there is nothing definite in quantum mechanics. Instead, matter can be treated as a wave. Okay, remember that the de Broglie wavelength of matter. Any particle can be described by a wave function. That means in order to describe a particle, electron, or any other particle in atomic and subatomic levels, the particle can be described by a wave function. What is the physical meaning of the wave function? Although we cannot determine the exact position of the particle, we can derive from it the probability that the particle will be found in a region of space at a given time. Again, this is based on Heisenberg uncertainty principle. We cannot exactly pinpoint where a particle is positioned. Okay, in the event of looking at the particle, the radiation we use in order to observe the particle will always cause the position of the particle to be uncertain. That's why the word uncertainty principle. All other observable physical characteristics, momentum, such as momentum, energy, and etc., are related to the wave function. So the wave function is not only can determine the probability of the position of the particle, but also the wave function will also relate to the observable. Observable means that we can observe it in experiment, such as momentum, energy, and other parameters. It is not possible to derive the Schrodinger equation from purely mathematical arguments. Okay, you cannot derive Schrodinger equation. That's why the equation is said to be a fundamental question. It's just like, for example, Newton's law. Okay, the three Newton's law of forces. So basically, they are fundamental in nature, and also some other laws in physics, such as the Maxwell's law and so on and so forth. Basically, those equations are fundamental in nature. So Schrodinger equation cannot be derived from any other mathematical expression, but basically it was like the Planck formula. Okay, E equal to H nu. It is out, inverted commas, out of the blue. Planck said that uh, uh, why don't we consider during that time he studied the black body radiation, the radiation emitted by black body as wave packets in discrete wave packets, and so on and so forth. So those were his hypothesis that basically should I say in inverted commas out of the blues. The same thing with Schrodinger equation. Okay, so it is fundamental equation. The only basis for developing a physical theory is that it describes experimental reality. So the basis for accepting Schrodinger equation, that the equation predict correctly. That means it agrees well with experimental results. It does make numerous correct prediction. An example, accurate description of the hydrogen atom. Accurate description of the hydrogen atom. Okay. Niels Bohr, of course, derive the energy levels of hydrogen atom, but in other things, the Niels Bohr postulates were not able to explain the full description of a hydrogen atom. But by using the Schrodinger equation, basically, the Schrodinger equation can accurately describe the properties of hydrogen atom. So in conclusion, a particle no longer has definite trajectory in space, only its probability to be found in a region of space in a given time. Okay, that's the conclusion, the main conclusion, that when we study quantum mechanics, we must have this in mind. Basically, we are playing around with probability rather than fixed position of particle. All observable physical characters of a particle is related to its wave function. Even though we are talking about particle, but the behavior of the particle can be described by a wave function representing the particle. Thank you very much for your attention.